All right, for our final lab, I just want you to experiment a little bit just to get a feel for how the links work. And there's a challenge at the end to see, just think a little bit more about your coding skills. I'm not an expert NetLogo coder myself, so I spent a little bit of time thinking about how I would accomplish a task related to programming network links to reestablish themselves. And you might have a very different approach, and my code actually isn't perfect. It just sort of demonstrates the idea. First, I'd like you just to go ahead and open up the preferential attachment model, which is based on the very kind of big name guy, Barabasi, wrote a book called The New Science of Networks some years back. Go ahead and just open the model up. I'm not going to read this whole slide to you, and just follow the instructions to look at the information tab, see if you can understand what the code's doing. And then just push the various buttons like redo layout, resize nodes. It's kind of really clever coding, and so one of the nice things about looking at this model is you can say, oh, I could use some of these tricks and borrow this code, adapt it to make things more visible on my model in some cases. Yeah, the main idea, of course, is that preferential attachment says the more attached you are, or a node is, the more likely a new agent would choose to connect to that one, preferentially as opposed to someone with very few connections. And this is what builds this idea of a scale-free network. And I just would challenge you to think for a minute, wow, are there situations like that? Are the nodes that are already connected the ones that you would prefer to connect to? I think you'll think of lots of situations where that could be the case. All right, so the last little part of this is what are the qualities? What does scale-free network mean? And you see the plot on the left of the degree distribution. A degree is the number of nodes. There's one node on this particular network with 181 connections, and all of the others are scaled down much smaller to much less connections. And the idea here is what makes it scale-free is when you plot this on a log-log scale, which is the right-hand plot, essentially the values on the previous plot become pretty much of a straight line. And that's kind of the test for the degree to which the network is scale-free. I'd like to encourage you to think a little bit more about the idea of what is a hub. And the resize nodes button provided in this model makes the size of the node proportional to its in degree, or its number of connections. And you can go in and right-click on that agent and inspect that one and find out the details of the hub agent. Or you could use the command center. Here's an example of a command which says one of the turtles with count of linked neighbors equal to the max count of linked neighbors. So everybody has linked neighbors, and if you have the maximum number, there could be more than one that have the same maximum number. So the result of this command is just going to randomly pick one of those, and that will find and highlight that hub agent for you. Just try that. Try that in the command line. Just for fun, of course, if you remove a hub, there's a lot bigger effect. So just experiment now using the command line. The code to remove a random agent just says ask one of turtles to die. So that's real simple code. Just type that in and you'll say, oh, one of the turtles. You can hardly tell that it happens if you've got a lot of nodes in your model. Now to take out a hub, one of the main hubs, the code uses that previous logic. Ask one of turtles with count of linked neighbors equals max, the same logic we described in the previous slide. Ask that one to die. Now if you do that, as this example shows, all of a sudden, instead of being a single connected network, there's a whole bunch of little fragments. The bigger they are, they're all called cliques. One clique down in the lower right-hand corner is pretty good size. Some of them are just individual agents, and you can see quite a bit of havoc is wreaked when you take away a hub. So the challenge, kind of the most interesting part of the lab really, is to say, well, how would you create or recreate a fully connected network once a single hub has been removed? So here's some ideas. I'll just talk my way through my thinking. I got this to work reasonably well. Start at one of the nodes with the largest number of connections left. It could have the same number as the one you removed, or maybe some number less than that. color that one orange. So now we know this is the hub we want to make sure everybody gets connected to one way or the other. Color all of the nodes connected to that one, say yellow, and then ask all these yellow nodes to ask the nodes to which they're connected to be yellow too. The idea is to get the entire clique to which this particular node is connected to be colored yellow, except not recoloring the focal node, which we will want to leave orange. Ideally, the coloring yellow process would be continued until every node in the clique is yellow. I couldn't figure out how to easily do this, and it's just my limitations as a coder. So I just, to illustrate the process, went down 2 levels, which isn't perfect, but works in many cases. I ran some experiments and found that it's pretty easy for this algorithm not to complete its task properly. So my thinking here is of some value, but not necessarily a good model to be followed. Once you've completed the previous step, then check all of the other nodes with the same largest number of connections, like the one you picked as your first focal node, and see if they are still red, meaning that they're not connected to the first one. If the next focal node is red, connect it to the orange node, and then recolor the red node yellow. Then ask all of the nodes connected to this new focal node, which was red and now we just recolored it yellow, to recolor themselves to be yellow if they're red, since they too are now connected to the overall network by virtue of their mate, their network mate. Ditto for all of their connections. That's down 2 levels, and really you should just repeat that till you run out. And I'm sure there's a way to do that in NetLogo. I just didn't figure it out. Then finally, starting at from the largest number of connections -1, now drop down from that largest size, a number of connections, just work our way down to 0, connecting up any other orphan cliques and coloring them yellow, as well as the nodes to which they're connected. So we just keep going down, ideally down n levels to ensure the entire clique is yellow. My code only goes down 2. The reason for this is if we don't make these now connected nodes yellow, then we might end up with some extra connections which would be erroneously made to them since they are now part of the network, but we forgot to go down and change them to yellow. So because they're red, they could get found later in the search process and be connected up to that initial orange node a second time. So there'd be 2 pathways for them back, which is no longer consistent with the objective, which was just to get every node connected into one large clique. All right, so using that kind of logic, and the code for that, the specific code that I created, is on the next 3 slides. And I'll briefly talk through that code, going into somewhat more detail about how we accomplish the kind of pseudocode task described earlier. You can then put a button on the interface tab to implement that code. You could also put a button on there that just does the removal of one of the hubs. Then you could quickly retest over and over again the relink logic by building a network, stopping it at some point, pushing the remove node button, followed by the reconnect button, and just see what happens. Does it kind of build a complete network? You can also resize and have it relay out the network to sort of visualize, did I get all the nodes, and did I create any duplicate connections? All right, so here's how it starts. So I called it to connect orphans to top dog. Let inmax, that's a local variable, be the max of the count of linked neighbors of turtles. So that's going to give me that largest number, either 1 or more hubs, largest hubs. Then ask one of the turtles that has its count equal to that inmax. So pick one of those hubs. Set its color to orange. That's our main focal guy. Ask its linked neighbors to set their color to yellow, and ask their linked neighbors, if their color is red, to also set their color to yellow. And that lowest thing there is another brace to close off all that logic. So now, ask turtles with count of linked neighbors equal inmax. Now we could get the same one. Its color was orange, so it won't pass this test. So if there's another one with that full largest number of linked neighbors, the inmax local variable we computed on the previous slide, if its color is red, then create a link with one of the turtles with color orange. It has to be one of now because we could have already found one. set its color now to yellow, and then go through that same process of asking its neighbors if they're red to become yellow, meaning I'm now connected into the overall network, and also ask their linked neighbors. You can see here that to keep this going down and to find a good stopping criteria probably is doable, but to illustrate it, I just went down twice, 2 layers. Finally, we set in. That's another local variable. Let in be in max minus 1. So we start walking our way down to smaller numbers of sizes of nodes. And while that number is greater than 0, we then ask the turtles with that number of neighbors, which is smaller than the largest clique that we found earlier, if its color is red, meaning we haven't already found it somehow in our previous process, create a link, hook it in now, with the turtle that has color orange, one of them, set the color to yellow, and then go through that process of asking the neighbors down 1 level down to set their color to level. Again, this should be n times down. So once we complete that process and we get all the way down to 0, it looks like I don't quite have all the code showing. If you look at the model, you'll see that I then set in to n minus 1 and keep repeating it until we complete that while loop. I didn't show quite enough code here, just the way it translated from PowerPoint over to Slidecast. So then when we get done with that, we should have brought all the nodes back in and connected and reconnected the entire network. So to provide just a very quick demo of this, let's take a quick look at the, we see the interface. This model has the connect orphan A logic that I wrote up, and it also has a remove hub button as well. So if we go over to the code, we can see that I'm just sliding down. The slider is a little bit off the screen. The logic that I've added is this: to connect orphans to top dog, which starts there and goes to the end of the model. The rest of it was logic. This logic here was already provided, which you might have looked through to see if you could figure out what was going on. And so what I did is I might do a setup and then go a little bit. Let me just go for a short period of time, and then remove one of the hubs, which, let me just show you that logic real quick. That just asks that implements that bit of code we talked about, max of count of linked neighbors of turtles die. So it just makes one of them die. The same code we talked about earlier. So I can remove a hub. Actually, let's first do a redo layout so you can just see how that works. You've already probably done this, and you get the idea that somebody's written this really cool code that just, it's kind of rubber banding code that tries to reduce the number of link crossing. It's not perfect either, but it does a pretty nice job. When you stop that, you can then resize the nodes, and we can see there's one big hub. So that should be the one that gets deleted when we remove the hub using that logic. Sure enough, it takes that away. And then if we do the reconnect orphan logic, it takes that hub and reconnects it up, and it kind of looks like it worked. We now have a color change here with them being that one being orange. But if we redo layout, it kind of pulls it in. Let's stop that, resize the nodes. I guess resizing it undoes it and redoes it. So it looks like in this case it probably worked. Now if I do a setup and I go a little bit longer and get a little more complicated one, there's a pretty good chance that my little bit of code won't work like I'd hoped. So I'm going to stop there, redo layout, just give it a little bit of time to get tightened up, and then maybe I'll stop there, resize node. So we now see again which node we want to delete. So we'll go ahead and run our remove hub and then see how we do with reconnecting. It picked this one over here. It looks pretty well connected up. Let's redo the layout, get that one into the center and see, did we miss anybody? It looks like that might have worked, and just on the surface of it I don't see any goofball lines. So You know, if you're really clever and you're enjoying this particular type of logic, you could see, well, what would I have to do with the instructor's attempt at this to generalize it so it goes down more than 2 layers as it's searching down through the cliques, coloring them up so we don't end up inadvertently adding. It looked like in most cases here, my going down 2 levels worked in a couple of cases.